So welcome everyone to this last session before lunch. Bear with me, I'm Stephanie, I'm a master's student at the University of British Columbia, and today I would like to walk you through my journey, a geographer's journey into AI, or more precisely deep learning. And together we will embark on this journey by virtually walking streets in Vancouver in British Columbia, mapping urban trees or the urban forest from street-level imagery. So this is a typical street-level image of Vancouver in spring. And just indicate by raising your hand who knows what species we see on this picture. Yeah, a couple? Okay, awesome. So these are cherry trees, also trees called, of the so-called genus Prunus. In tree classification, we generally differentiate between different species, for example, the sour cherry or the sweet cherry. And these different species are all found under one genus, in this example, the genus Prunus. And today we're going to classify up to 43 different genuses from images like this. If we walk a little further, we also see trees like that one on the right. And who thinks that this tree is from the same genus? Raise your hand. Okay, why do I ask? Of course, it's not the same genus. This is actually an apple tree, also belonging to the genus Malus. And this little example shows you how much of a fine-grained classification problem this can actually be. So the ultimate goal of this project was to develop a tool that allows us to first detect trees, then locate them, and lastly identify the genus of these trees from street-level imagery in order to create maps of biodiversity in different cities in Canada. So why is this important? A very good example is we need maps like this for biosurveillance to try and identify hotspots of possible invasion outbreaks early. So just imagine in Vancouver we have a threat of sudden oak death to arrive there through international trade. As the name suggests, sudden oak death mainly attacks oaks. The only possibility to detect this threat is to actually go out and visually inspect trees, especially located next to ports or other high threat areas like industrial zones. And for this, we need pretty fine-grained information of where we can find these oak trees. So why take the plunge into deep learning here? Traditionally, the most commonly used method to generate maps of urban tree biodiversity is actually by manually collecting this data. So biosurveyors or tree experts going out into the field, measuring GPS points and identifying the trees. This is, of course, a very time-consuming job and very expensive as well. So in order to support municipalities that just simply do not have this money to generate and collect this information, we need different tools. So again, why taking the plunge into deep learning? Deep learning actually opens up the possibility for researchers like me to use data sets that we traditionally neglected, like street-level images, because it also takes a lot of time to analyze information from street-level images. And the second trend is that we now have open source projects like, for example, FastAI or Keras that make it really easy for scientists like me to start learning how to deploy and train deep neural networks. And in the next couple of slides, I would like to show you how our workflow for urban tree mapping looks like, which lessons we learned in choosing deep learning models, in generating our training data, in training the models, and the results we achieved. So the first question we asked ourselves, because we actually wanted to deploy this, what do our users need? In this case, different types of researchers and different governance agencies and so on. And we decided after a couple of interviews that we will separate our tool into 3 different modules, namely our tree detection module, our tree geolocation module, and our tree classification module. We do this because some research projects might need only detection and geolocation. Others might need only detection and classification. To start, what we asked ourselves was which deep learning models are actually state of the art to tackle these tasks, and then also very importantly, which models are openly available for us to access and which ones are pre-trained, because that makes training and also basically data generation for us a lot easier. So for our tree detection module, we chose a model called mask-RCNN, which can be found implemented by, I think, Matterport in GitHub. It's a state-of-the-art instant segmentation model. That means if we input our street-level image, we return a bounding box around every detected tree, a mask around every detected tree, and a softmax probability how certain the model is that this is basically a tree. Our second module, the geolocation module, leverages monodepth, which actually is a readily available trained deep neural network. It returns a dense depth layer of the input, which basically means we can now use the masks generated in our detection workflow to extract a single depth value for every detected tree. What does that mean? Usually street-level imagery comes with the information where you took the image in GPS locations. So we now know the GPS location, and the depth gives us the information how far the tree is actually away from this specific location, and we can make a rough estimate where this tree is actually positioned in space. If you use something like Google Street View or also Mapillary as an input for your imagery, these images are usually taken roughly every 10 meters, which means we can detect one tree multiple times, because one tree is roughly on 8 images. We therefore can leverage triangulation to, first of all, get rid of these multiple detections and also improve our detection accuracy. And this geolocation module will return GPS points. The third module we run is our classification module. We trained a normal CNN classifier based on ResNet 50 in FastAI to differentiate our 43 different genuses and the one other class. And again here, this classification module takes as an input a tree of a picture of a single tree, which we generate by simply cutting the input image by the bounding box we generate in the detection module. So together, the GPS point and the genus label allow us to generate a map of urban tree biodiversity. Okay, so now we decided on which models we will train. How do we actually get our data? And no, we actually don't need these millions of training examples, because, like I already suggested, we leverage transfer learning. Transfer learning basically means you initialize your training process with a model that has been trained for different tasks. Usually these models come with weights, and these weights are saved in HDF5 format. So if you ever look for your own model and you look on GitHub and there is a repository with an HDF5 format file, the chances are good that this is a pre-trained model. Because tree instant segmentation still is a difficult task, we decided to look for more data, actually leveraging already published data sets that contain semantic labels for tree instances. There's one data set out there called Common Objects in Context Stuff, which contains roughly another 36,000 images. with semantic labels for trees. So a semantic label means every pixel is basically classified. So you can't detect objects, but you know what pixel is which class. So in the second training step, we trained our mask RCNN model with this semantic cocoa stuff class. And because we also want to differentiate between different tree objects, we now went out and labeled roughly 60 images ourselves. These 60 images were picked randomly all over Vancouver and the city of Surrey, and we generated around 800 tree masks. So just for your reference. Okay, now we have our models, we have our data. How do we actually learn? And since this morning it seems like there's no talk without XKCD, here's my XKCD comic. So XKCD seems to suggest that now that we have the data, we just pour it into our bunch of linear algebra. If the answers still look wrong on the other side, we just keep stirring until they look right. Not much else to add, right? So the only thing I would suggest is keep track if you're stirring left or right from the beginning. So if you start your experiments, there are open, amazing open source packages out there, for example, MLflow, TensorBoard, which can also be implemented for PyTorch, or simply Jupyter Notebooks if you use FastAI. It's your choice, just make sure you keep track right from the start. So since we talked about tree masking before, this is an example of how we trained our tree genus classification module. Herefore, we used FastAI, and FastAI is an amazing open source library for everyone who has not done deep learning before to get started. It's relatively great for scientists like me because it includes best practices right in their high-level API. So there's not much you can do wrong at the beginning. Here we see we can actually initialize training a model in only 6 Jupyter Notebook code cells. Including heavy data augmentation, including fine-tuning the learning rate, and including using one-cycle scheduling for the training. We noticed that for our use case, actually in training, the biggest improvements were iteratively cleaning our data set and also really fine-tuning the augmentation process. So even if we talk about training, it's actually the biggest impact you can make on improving your model's performance is by improving your input data. In our workflow, at least. So the other problem we had is we had a very imbalanced data set, meaning we had, for example, 10,000 pictures for the ASA class and only roughly around 100 for other classes. This is a problem for most neural networks, and we solved that simply by oversampling classes where we had only a few images, so we more or less just copied the images with a little bit of augmentation applied, and by undersampling really big classes. So you, for example, reduce the 10,000 images to only 5,000. That was another step that helped us a lot improve our model performance. And the last one was applying something called mix-up. I'm not going into detail what this is. I'm happy to answer any questions about it later. I just wanted to show that in FastAI, it's so easy to implement mix-up that you actually basically just have to do the callback learn.mixup, and your mix-up is applied. So again, here, if you are just starting out, FastAI is a great way to do so. So how do our results look like? For tree detection, remember we masked images for the areas of Vancouver and Surrey, which means the final images we trained on actually only contain trees from the shape which you can find in the Pacific Northwest. In green, we see a score for Vancouver, and in purple, we see a score for Surrey. So additionally to that, we tested our tree detection module on imagery of Pasadena. Pasadena is roughly 2,000 kilometers south of Surrey in Southern California, a completely different ecozone. And for example, we also find palm trees there, which we do not have in Vancouver. And lastly, all of these 3 previous data sets were generated with Google Street View. We acquired some data from a company called Mapillary that does similar things to Google Street View, but uses, of course, different sensors. And Mapillary imagery was acquired from the city of Coquitlam, which is relatively close to Vancouver and Surrey. But comparing the results for all 4 data sets, we actually see that our model generalizes really well. And it doesn't, and that, of course, there is a difference in image quality, and image quality actually matters. But in terms of tree detection, you can apply it at least for these 4 cases. We also noticed that the bigger the tree mask is, the higher is the score of our evaluation metrics, which means we can now go out and recommend our users how ideal input imagery would actually look like. And lastly, we decided to implement a post-processing step to exclude all trees that are smaller in size than 3,000 pixels in our geolocation and classification process. These were mostly the trees you could see over rooftops far, far in the back. So they were not very informative for mapping in this case anyway. These are the results we generated for our genus classification deep learning model. And looking at the confusion matrix, we see that our model generally performs well in classifying genuses. But we also see that there are still a couple of classes that don't have very good classification accuracy. One of them is Stervatia, which you see there on the right. And Stervatia most of the time gets confused with Crataegus. And this has 2 reasons we analyzed in our case. First of all, Stervatia was one of the cases where we unfortunately were not able to acquire a lot of training data for. And secondly, even for experts, it's actually pretty hard to differentiate Stervatia and Crataegus. So we conclude that generally there are a couple of classes you can use this model out of the box for. There are a couple of other classes, if you're interested in the genus Stervatia, you might consider training the model a little bit more. So to conclude, deep learning for us opens up the possibility to analyze data on scale that has previously been neglected or was very time-consuming to analyze in all sorts of research fields. And open source projects like FastAI and Keras now enable scientists like me to actually train and deploy deep neural networks. And we, in this case, used FastAI, Keras, and TensorFlow to build and deploy a tree detection, geolocation, and classification workflow and map urban tree biodiversity. And with this, I say also thank you to all parties involved in this project, and thanks to you. And if there are any questions, I'm happy to answer them now or later, or feel free to shoot me an email anytime.
Thank you very much. Got a question right there. Okay, and then.
Thanks so much. So I had never heard of mix-up until 10 minutes ago, but now I'm reading about it. I'm just curious if you were able to quantify in any way, perhaps by comparing R-squared values, what did mix-up buy you? Could it increase your R-squared from 0.78 to 0.82, or I'm obviously making that up, but do you have some other way in which you can quantify how much mix-up helped you?
Yeah, so in our case, we basically started slowly implementing all of these steps I showed before. So we started from like nothing, just the raw data, then we implemented clean data, and so on and so forth. And with Mixup, we gained roughly, I would say, around 6 points in accuracy. But also, we gained a lot better, our recall and precision actually got a lot better. So the matrix looked a lot nicer afterwards. And yeah, basically.
Hi. I had a question about the timing of the year in which you took the pictures or grabbed the pictures from. I'm from Philly, and so we have lots of types of trees that will drop all their leaves during the winter, so you're just left with barren branches, whereas in the summer, you've got full bloom. You can easily detect that it is a tree. So did you come across difficulties identifying trees because of the time of the year that the Google Map images were taken?
So we actually really tried to build this tool for urban forest practitioners, and most of them basically told us that they might not be able to use Google Street View imagery, but they would need to generate this data on their own, which is also not hard because in the end you can, like Google Street View does it, stick a camera on top of a car and take your own data. And they told us that they mainly need to check trees with leaf-on conditions. So we generally neglected this leaf-off condition a little bit. But we did assess the model for this, and funnily, we found out if there's sky in the background, we can definitely detect the tree with leaf-off condition. If there is a very complex building in the background, it doesn't pick up on the tree. So that would be something to improve later on, potentially, if there's the need. Yeah.
Thanks. Hi, I was wondering if you've maybe considered testing out your model in other regions of North America where tree diversity is higher, such as like the Southeast, just to maybe get like a better idea if like there's particular like genus or species that might confuse the model.
So partly, I'd be very interested in that. I know that so the Canadian Food Inspection Agency, who is doing the biosurveillance, is particularly interested in 10 genuses because they are very important for the Canadian forestry industry. So we mainly focused on them, and then everything on top of that was out of our own interest. But it would be a cool project, I think.
Hi, thanks for your talk. I also found my way into deep learning through geography, so it's really cool to hear your story. I was curious what labeling tool you used for the images that you did manually label.
Mm-hmm. We used Labelbox, which is proprietary software. Generally, they have research licenses, and we were quite happy with the tool. It made it pretty easy.
Okay, great. Let's give our speaker another round of applause.